Hello and welcome once again for another Advanced Engineering Mathematics video. This is Day 1, Part B. So, for ordinary differential equations, there's actually this concept which is really useful, and we'll get to more of it as this course goes on. And this idea is of a geometric type of interpretation of differential equations. So how we can actually find this geometric type of solution, it's not a solution per se, but it allows us to visualize all solutions. It's so powerful that we don't even actually have to know what the solution is, the actual explicit solution is, in order to use this technique. So there will, as we'll see at some point in the course, there are actually differential equations that we don't even know the solution to, which is obviously a problem. And typically if we want to estimate solutions, we then need to use some kind of numerical method and whatnot. But at least in this case, we can actually visualize roughly what the solution must be, what the solutions, all of the solutions must be in the xy plane, or it could be higher dimensional, of course. But for now, we're going to focus on first order ODEs, which will allow us to look at a plane. So first, we're going to take the explicit form of this ordinary differential equation, which is written in the form y prime equal to f of xy, right? So we have some function of x and y, and it's equal to the derivative. Now notice what this does for us, though. By writing it in this form, then we actually can see that because the left-hand side is a derivative, that means that the right-hand side is the derivative as well. We're going to use this to our advantage, because now we know that this is going to be the slope of the tangent line, right? So at any particular point, we actually know what the slope of the tangent line has to be. It's whatever is on the right-hand side. So we can, if we know what the value is on the right-hand side, then we can get an estimate, or we know exactly what the slope has to be at that point of the tangent line of any solution there. This is fantastically powerful type of technique, and I want you to really think about what this means here. So if I'm given some point, x naught, y naught, then I know when I plug in those values, x naught, y naught, into the solution here, the function over here on the right-hand side, then I get a value which tells me what the slope is at that value of any solution that passes through there. And what we can do is we can actually express this in terms of little lines, which we'll call the vector field. So this is known as the vector fields. This is a technique that is useful for many, many reasons, as I've already mentioned. One of them being that you can actually get a visualization of what's going on, and the second being that we don't even need to know what the actual solution is, because this helps us visualize, regardless of what the solution is, what the solution kind of must look like. So you can actually choose a grid in space, and at each point make little line segments that represent the slope at that point. So here's a simple example: y prime equal to x times y. Well, if I know that y prime is equal to x times y, then I know that the slope, which is over here on given on the right-hand side here, x times y, will be that value, the slope of the tangent line at that particular point. So you can imagine, for instance, that if either y or x is equal to 0, then the slope has to be 0, right? Because 0 times anything is 0, so the slope, 0 times any number, is 0. And so the slope there has to be 0. So this is true along both the x and the y axis. Now on the x-axis, it's kind of silly. It's hard to actually see those lines, right? Because you're laying right on top of the x-axis. But on the y-axis, obviously, the slope being 0, they look like little tick marks, as we'll see. Notice here, I'm drawing the vector field here, and notice here that these little blue lines, those tick marks are the slope at y equal to 0, right? At x equal to 0, excuse me. Those are the slope at x equal to 0 as I go up and down this curve here. So obviously, because that line has a slope of 0, I'm going to draw it as a flat line, because that's the slope of a curve or the slope of a line being 0 means that it has to lay flat, right? Like it has to be parallel to the x-axis, okay? And similarly, that'll be the case down here, and I kind of tried to draw it a little bit. It's hard to see because it sits right on top of the x-axis, but that's true of any solution down here on the x-axis as well, because again, when y is equal to 0, the slope has to be equal to 0 of that solution line. Now, if I choose just a particular point, say x is equal to 1 and y is equal to 1, which is right about here, right? At that point, I should have a slope of 1, because 1 times 1, x times y, 1 times 1 is 1. And similarly, 1 times 2 is 2, so the slope should be a little bigger, and I tried to show that here. But the slope is a little larger, it goes up a little, it tilts up a little higher, and so on, right, as I go along this way. And similarly, along this axis where I'm holding x constant, I should see as I move up the y-axis that it gets larger. Now this, over in this side, I'm going to have a negative slope, because one of the values is going to always be negative, which is x, and one of the values is always going to be positive, y. So in this quadrant over here that I've pointed out, I'm always going to have a negative slope. Down here I would have a positive slope again. I didn't draw in the lines there, but you could definitely do them yourself, the little line segments. And over here again, it's going to have negative slopes, because the y value is negative and the x value is positive. So when they multiply each other, they become negative, and so on. So this technique is actually really powerful, and we'll do an example or two to show how we can do it. The nice thing is that there are available out there such things such as Sage Math, which is completely free, and it's called a computer algebra system. Sage Math is a very big library, and you can code in it and using Python language, which is nice, and obviously Sage Math's own built-in stuff. But there exist other computer algebra systems, so you don't have to. You can pick whichever one you like, and many of them are free, although some of them are not free, and you can obviously make your choice on whether or not you want to purchase a system such as this or not. That I'll leave to you. But there are plenty of computer algebra systems, and they will actually plot this if you give them what the derivatives are of the particular equation. That's all that I have for this video. Hope to see you again soon.